All right, lesson 2.6. So we have section 5.6 and section 5.7 left to do, and then we're done this unit. All right. So here we're going to talk about properties of linear relations. Linear, right? We're talking lines here, straight lines. The graph of a linear relation is a straight line, right? When a linear relation is written as an equation, it will contain one or two variables and its degree will be 1. Okay? The degree of a polynomial is the highest exponent, right? So if you see, just one variable and a number, that would still be linear. Okay? Here there are two variables, but none of them has an exponent that is greater than 1. It's still considered a linear. Here you have, two variables. You have a fraction as a coefficient, -1/2 x, but still the variables themselves, they only have an exponent of 1. So all of these are examples of linear equations. Non-linear would be anything, right? Here you have an x squared. Maybe I'll highlight that, right? X squared. Here you have k squared. Here you have x times y. X, y, also not linear when they're multiplying like that, okay? So all of these are examples of non-linear, meaning their graphs, or their graphs could look like this, right? They could look like this. They can look like this, right? They are curved, right? Linear. Actually, x is equal to 7 would be a vertical line like that. You'll talk more about that. Anything with two variables either slants up or down, okay, and so forth. So I'm not going to do more than that, but linear is always like that. Non-linear curves, okay. So there's something particular about linear, that there's a way we can know for sure if it's linear, right? You can determine whether a relation is linear or not from a table of values. That's actually, you can, this is if you don't have a graph, right? If it's a graph and you have a line, it is linear, end of discussion. But let's say you have a table of values like this, or let's say you have a bunch of, because face it, these are all points, right? Like this relation here would be 0, 0, comma, 2, 6, comma, and it would keep going, right? That, like, all the way to 824, right? So it could be a table of values. It could just be a set of points like that. They're saying the exact same thing. We could do our arrow diagram, right? Where we had the x's here, the y's there, and then pointing with arrows to the other side. But anyways, the way we check for linear relations, right? The values of y increase or decrease by a constant amount, as the values of x increase or decrease by a constant amount. Horizontal and vertical lines are exceptions. But here, I want you to highlight the fact that, right, the y values increase or decrease, I got a new highlighter, by constant amount, okay? The values of x increase or decrease by a constant amount. That's how you know something is linear, okay? So in this case, the work has already been done. You notice that every time you move up, you're going up by 6. There's a constant, right? Constant y value, sorry, constant y value. Then check for x2. It's going up consistently by 2s. This is easy to recognize. If the values are a bit bigger, what you do is always, right, you take 6, you subtract it by the value that's before it. So 6 minus 0 is 6. 12 minus 6 is 6. 18 minus 12 is 6, right? So every time you subtract the current from the previous, you know how much you're going up by. Same thing here, right? 2 minus 0 is 2. 4 minus 2 is 2. 6 minus 4 is 2. That's always 2, right? So this would be linear, right? Linear. Linear, comma, since x and y increase. In this case, is increase. by constant amounts. Okay. Here we go. Example 1. Does this table value represent a linear relation? So they're basically asking you, without graphing, would this produce a line, a straight line? Okay. So we check, right? We're gonna check here. Here we notice that it's going up by 2. That's important to recognize what's happening, right? You're going up by 2 the whole time. And it's constant all across. Even if there was one jump where that wasn't the case, it would not be linear, okay? Here, what do we have here? We actually increased by 4. From here to here, we increased by 20, right? 25 minus 5 is 20. Here we increased by 100. And then here we increased by 500. Actually, you could have stopped right here. You went from 4 to 20. That's already not, it's not a constant increase. It's going from 4 to 20, then 100, then 500. So it's not, the changes, we're going to summarize this by saying, right, the changes in the first column are consistent or constant. Let's be consistent and call it what we called it earlier, constant. But the changes second column are not. This does not represent a linear relation. Okay. So there we go. Next, example 2. Does this set of ordered pairs represent a linear relation? In a sense, you could be writing this as a table, right? But we just need to make sure. Let's look at the x values, right? From -9 to -7, what happened there? It went up by 2, right? From -7 to -5, we're just looking at the x values here. It's almost like looking at the x values here. We went up by 2 as well. Here, we go up by 2. Here, we go up by 2 as well, right? So you're going from -9 to -7, -5, -3, -1. What would come after this? You would have to have a +1 here if you wanted another point. If I asked you, like, fill in the blank, what would have to go here for the x value? Well, you would have to add another 2. You'd have to continue the pattern. Let's look at the y values. From -5 to -10 to -5, we went up by 5. From -5 to 0, we also went up by 5. So it seems as though we're going to be fine, right? It's a linear relation. Yes, relation is linear. Changes for x and y values are constant. Okay. Yes, relation is linear. Changes for x and y are both constant. So that's how you determine that, right? Linear relations involve variables that change at a constant rate. We can find the rate of change. Okay, rate of change, we're going to call that slope later on. Okay, rate of change is when we're talking about specific a context, or there are units involved, right? Rate of change of a linear relation, right? And the rate of change must be expressed with its units. Okay, it's very important. Make sure you know that if it's a rate of change, you know that you have to add units to it, okay? And make sure you understand this. It's going to be a bit of a theme moving on to the next chapters. The rate of change, right, is equal to the change of dependent variable, or the change in the dependent variable over the change in the independent variable. So I'm going to rewrite this and shorten it a little bit. The rate of change can also be looked at as, this is the change. Delta is the change of the dependent in the dependent variable over delta of independent variable. You can also think of it as the change in the y values over the change in the x values. Okay, I'll tell you the classic rate of change. A classic rate of change is speed, right? 100 kilometers per hour, right? It's 100 kilometers for every hour that you're driving. That is a rate of change, okay? Independent variable is plotted on the vertical axis. Independent variable is plotted on the horizontal axis. That should not be any news, right? This is just basically saying x goes here, y goes there. Independent, dependent. Okay? And we're going to do the rate of change. Example 2. For example 2, this example here, we're going to do the rate of change there. Rate of change would be dependent over change and independent. And what would that be? The change in the dependent variable, that's the y, right? Changes in the y values. Because remember, every ordered pair, the second entry is always the y value. You're dependent. So there you changed by 5 every time. And your independent variable, your x, always changed by 2. Exception to the rules, right? No units provided. So if they don't give you units, obviously you can put units, attach units to it. All right, let's keep going. Example 3. You know what, I'm going to stop this right here and then just continue, make a new video for this part. So just hang in there.